Welcome everybody to the third season of the Isogeny Club. I hope that what I'm saying is actually coming through. We are in Quito for Latin Crypt, hence why I'm here with Luciano. And today, actually, we have a very exciting talk, Modular and Formal Orientations Beyond OSIDH by Leonardo Colò, and he's now at the University of Waterloo. So Leonardo, you can start if you want.
Yeah, thank you very much. Can you all hear me?
Yeah.
Okay, cool. Yeah, so thank you very much, Jonathan and Crean, for inviting me and for chasing me for the title and the abstract. So yeah, I'm gonna talk about modern formal orientation. And well, the title I gave and I wrote here and I gave in the abstract was Beyond OSIDH. I actually wanted it to keep it as general as possible because I would like to cover a lot of material, which might seem scary, but well, let's see how it goes. So this is a joint work with, and pretty much a very work in progress with David Coel, University of Marseille, where I was during my PhD years. So, wait, okay. So let me just give you a very sketch and brief list of contents. So I'm gonna start by reminding what an orientation for a supersingular elliptic curve is, and how we get a class group action on the supersingular isogeny graphs. And well, for most of you, probably all these slides look already familiar, but I just wanted to be sure that we are on the same page with the notation and with the terminology that I'm gonna use. I'm then gonna pass to introduce very briefly the OSIDH protocol, which is the protocol we proposed using orientation, which is pretty much a general framework to look at supersingular elliptic curves rather than a very effective cryptographic key exchange protocol. And then I'm gonna propose the two directions we have been exploring lately, which are the idea of adding level structure to our construction, and the formal orientation approach, so the idea of using formal groups to transmit informations and data. I'm not sure how much I'm going to be able to say about formal groups. So as I was saying before, there's the talk of David, which David gave at CM conference in Eindhoven. So you should be able to find the video. So what I'm going to do is I'm probably going to give the background on formal groups and the general idea that we would like to use in the OSIDH framework. And then maybe if I'm not able to cover all the details, I'm gonna refer to David's talk. So let's see how much time I have. Okay, so let's start with orientations and class group actions. So first of all, well, the setting is always the same. So we are working with supersingular elliptic curves. In particular, we're gonna look at supersingular isogeny graphs, which are normally complicated objects, which makes them a very suitable candidates for cryptographic applications. But of course, I mean, this complicated shape comes from the fact that we lack a commutative class group action, as in the case of ordinary elliptic curves. So in order to overcome this situation, we propose to endow the set of supersingular elliptic curves with some extra structure, with some extra piece of information, which we call orientations. So if I remember correctly, the exact first talk of the last season was about orientation by Sarah. So I'm just gonna briefly recall the terminology. So suppose we have a quadratic imaginary field K, and suppose we take a quadratic imaginary order O. An orientation by O is just an embedding of this quadratic order inside the endomorphism ring of our supersingular elliptic curve. And now a K orientation is just an embedding of K, so the quadratic imaginary field, inside the endomorphism algebra of our supersingular elliptic curve, which is just a tensor product of the endomorphism ring and Q over Z. And now we say that an orientation is primitive if, well, basically these two definition agrees, which means if the image of O is actually isomorphic to the intersection of the image of K and the endomorphism ring of Q. What's nice about this construction is that the category they're going to obtain, so the category of supersingular elliptic curves with this extra piece of information, becomes equivalent to the category of ordinary elliptic curves with complex multiplication by k, which means that we can recover the terminology that we have for an elliptic curve, the shape of the volcano as in the isogeny graph, the idea of horizontal, ascending and descending isogenies, and in fact, the class group action. So I just show you how to orient the object of this category, so the elliptic curve, the vertices of our isogeny graph. Let me just briefly tell you how to orient the map in the category or the edges in the isogeny graph. So what does it mean to orient an isogeny? So suppose you have two elliptic curves connected by an isogeny, and suppose that you have an orientation on the first one. Then you can transmit this information through the isogeny just by composing and precomposing your embedding, so your orientation with the isogeny in its dual, and then normalizing by dividing by the degree. And now suppose that you already have an orientation on F. We say that the isogeny itself is oriented if the pre-existing orientation on F agrees with the one coming from E through the isogeny. So this is an oriented isogeny. So this gives you the complete description of the category we will be working on. And just as an example of what happens when we endow our supersingular isogeny graph with this orientation, here we are working over P equals 71, which is has just a nice feature of having all the supersingular J invariants defined over FP, which makes things just nicer to represent. And so we have J invariant 0, which is defined, which is supersingular of F71, and we are orienting this object using Eisenstein integers, so cube rooted. And so on the right here, you can see the standard classical non-oriented supersingular isogeny graph, while on the left, you see the resulting thing when we endow this with the orientation structure. So there are, of course, many differences. The first one and the most important is that, well, the first one is that, on the left, you can recognize the classical shape of the volcano that you have in the ordinary situation. But the most important difference is that while this graph on the right is actually finite, the graph on the left is an infinite descending volcano, which means that it will appear multiple times, and also it will appear multiple times at a certain level. So you will, if you descend long enough along the side of the volcano, you will get to find the same J invariant appearing multiple times at the same level. And so this is covering of your standard graph. So just to highlight once again what I just said, here is another example. This time I'm looking at the volcano from the top. So again, we're working over 71, but this time we are orienting this object by some class number 5 order, which is the maximal order inside Q square root of -79. And here I'm just highlighting in green the J invariant 17, just to show you that in fact it appears multiple times already, at different levels, like here and here. But you can see that 17 appears.
Sorry,
can you hear me?
Yeah, I think you just disconnected for a second.
Yeah, I don't know what happened, actually. I'm really sorry about that. Well, let me share them again. Where are they? So can you see that?
Yes.
Yeah, I'm really sorry. I don't know what happened. Okay, so yes, this was the standard example. And let me just briefly say that, in fact, the idea of endowing, sorry, I'm just opening the chat again. I forgot to say, if you have any question, just interrupt me at any time or write in the chat. If I don't see it, please, Jonathan or Green, tell me. So yes, the idea of endowing supersingular elliptic curves with orientation was exactly to be able to recover this class group action. So here, the class group action is described exactly as in the ordinary case. So it takes an ideal and an ideal in the order we are orienting the supersingular elliptic curves with, and an elliptic curve, and it sends it to E modulo EA. And we recover basically the same theorem that we have in the ordinary case, saying that, in fact, the set S is OPR, which is a set of supersingular-oriented, primitively oriented curves, is a torsor for the class group CLO. Here I'm writing rho instead of P because, I mean, this theorem is true once that you have fixed an embedding of the quotient of the endomorphism ring modulo P inside FB bar. But once that you have set or chosen or fixed this embedding here, then you get the classical theorem, which tells you that there is a faithful intransitive action, and therefore there's this bijection, which is exploited, for example, in the classical ordinary key exchange protocol or in C-side. So, okay, so let me show you briefly how we are going to use this class group action. So we are going to, set the easiest possible case, which means we are going to take an isogeny chain, normally descending on our volcano, and we are going to use very small primes, L, like 2 or 3, and we're going to start from a very specific supersingular elliptic curve, like J invariant 0, J invariant in 728. And even more, we are orienting the first elliptic curve by a very, very special class number 1 order. For instance, Eisenstein integers or Gaussian integers. Now, if we use the action that we have, that I just described before, this gives an horizontal isogeny. But since here we're working with class number 1 order, this means that you're actually walking along the crater, which consists of only one vertex, which means that the resulting action sends E0 to E0 itself, so you get an endomorphism. And it might happen that the same thing is true if you walk one step down by pushing forward this orientation, the way I showed you before. But at a certain point, if you do it for enough steps, you're going to distinguish the action of the primes determined above Q. And so you can push forward this action along the whole chain and get something significant at the bottom level. So in some sense, what we are trying to do is sort of replicate C-side, but instead of using only supersingular elliptic curves that are defined over FP, we would like to use all the supersingular elliptic curves, even those defined over FP squared. But to do that, we actually have to do some intermediate step in order to then be able to replicate the picture at some level n. Sorry, Q is just a split prime, exactly in C-side. I'm sorry, I forgot to mention. Thanks. So Q is just a split prime, which then we use to apply this action here. So in fact, when you apply the action by Q, you actually distinguishing between the 2 primes above Q. So which one will give sort of like positive direction and which one will give sort of negative direction. And this choice can be pushed through all the chain in order to get a positive or negative direction at level n on the final elliptic curve En. So let me just show you how the protocol works. And maybe then I'll do a visual example. So maybe I will clarify most of these things. So the protocol works as follows. So exactly as in the setting of before, we have a descending L isogeny chain of some length n. And again, the prime L is very small. The first elliptic curve is very special. And we have a set of split primes, exactly in C-side, as in C-side. And then Alice and Bob will choose their secret key, which as in C-side comes in the form of the exponents of these primes, chosen in some bound. And then they will do basically the same construction that I showed you before. So they will construct this that we call the ladder, which is this descending commutative diagram, by simply acting with these primes on the first elliptic curve and then pushing forward this information along the chain, which can be done just by either pushing forward division polynomials or, as I will talk about later, by using modular polynomials and therefore like completing square by solving systems of modular polynomials. But we will talk about this in a moment. So in the end, what they will end up with is a bigger diagram than that, but they're secret path will be the path from the final supersingular elliptic curve En, which is public, as it is the whole chain, and their final elliptic curve, which would be Fn or Gn. So now we are facing a problem, exactly as in OSIDH. So passing just the data about the final elliptic curve is not sufficient. We have to pass some extra data. And in OSIDH, this comes in the form of the pre-computed positive and negative directions for all the primes that we're using at the final elliptic curve of Alice and Bob. So once again, I'm going to give you an example in a moment, but basically when you end in Fn, you also have to pre-compute a further step in the two directions that you are taking for each prime and passing these neighboring curves to the other party in order for the other to be able to determine which direction you are considering positive and negative. So which of the two primes above P you are using as a positive action or a negative action. So you exchange all this data with the other party, and the other one, using the information he got from you, he will recompute another big ladder and being able to end up with the same final elliptic curve. So let me just give you an example, a very visual one. So probably some of you have already seen these pictures, but I think it's pretty nice because it gives you a visual representation of what I just said. So here we're working over 10,007. Again, this is a two isogeny graph. We have 0 here, and we are orienting it by the Eisenstein integers. And we are taking 13, 31, and 43 as three split primes, just for example. So Alice chooses as a secret key 532. So now on the right, you will see what happens on the isogeny graph, and on the left, you will actually see the construction of this commutative diagram, so of our ladder. So she will, apply 5 times the prime L1, and then she will store or pre-compute the next step, doing the same exact computations, but this is the information she has to pass to Bob. So now she does 3 steps in the L2 isogeny graph. 1 time, she also have to push forward the information about the positive direction of the previous prime. And then 3, and then she will store like the next step for L2, and then do the same for L3. So 1, 2 steps, and then store the positive direction for L3. So now we're going to focus on the last level of this volcano here, and we see what Bob does when he receives the information about the final elliptic curve of Alice and the positive directions. So this again is the final circle of the volcano on the right, and on the left you will see once again the construction of the commutative diagram by Bob. So Bob, for instance, chooses 312 as a secret key. So he will work 1 step in the positive direction for L3, and the positive direction is the one he received from Alice. So it's this one. And then he has to push forward the information that he received from Alice about, well, the positive direction for L3, which basically is the next action of the same prime. And then he will construct a sort of like commutative diagram to obtain the positive direction at L2, and another commutative diagram in order to get the positive direction at L3. And then he will work another step in the L1 isogeny graph and push forward information. And then the third one, pushing forward information about the 2 next primes. Then he only has to work 1 step in the L2 isogeny graph, push forward information about L3, and then 1, 2 in L3, he will end up with this elliptic curve. And now let's see what Alice does. So this again is Bob. 312 was the secret key. So 1, 2, 3, positive direction, 1, positive direction, 1, 2, positive direction. And he will pass this information, so final elliptic curve and neighboring curves for the 3 primes he chooses, to Alice. And so this is what Alice sees, the final elliptic curve of Bob and the 3 direction that he has. So the secret key of Alice was 532, 1, 2, 3, 4, 5 in the positive L1 direction, then 3 in the L2 isogeny graph, 3, and then 2 steps for L3, 1 and 2. She will end up with this final elliptic curve, which was exactly Bob's one. So everything works with the problem that we are actually sending a lot of information to the other party, because we're sending the final elliptic curve plus a lot of neighboring curves. So like this is just a toy example, so I just use 3 primes, but normally you have like 20 or something like that. And you also walk much farther in the isogeny graph, so you get to a much deeper level than that. So all the constructions of the ladders takes definitely more time. So just very briefly, some security considerations. I'm not going to spend too much time on that, but I can give you all the details later if you want. So the security of this protocol is basically relies on this composition of maps. Here you have on the right this set of supersingular elliptic curves without any orientation. So this is a classical set. Here you have the oriented set. And here you have the key space where you have where you pick your exponents. So in some sense, you want this map on the right to be surjective, because you would like to be able to cover as many elliptic curves as possible, which was actually one of the reasons why we started working on an OSIDH, because we wanted to somehow overcome the idea that you have in C-side that you were working with just those defined over FP. And then you want the first map, the one on the left, to actually be injected, because you don't want to get too many collisions. So in some sense, you would like both these maps to be injected, because again, you don't really want to get too many collisions here. So you don't want to see too many times the same J invariant appearing at the same level. But in fact, for the map on the right, surjectivity is much more important. You can actually try to look at sort of like right balance, but injectivity and surjectivity of the map for the map on the right is completely infeasible. So you start losing injectivity when you are covering about half of the supersingular elliptic curves. So in some sense, we prioritize surjectivity for this map, but we definitely want injectivity for the first map here, because if you lose injectivity, then you can use the attack of Pierrick and Luca that in fact exploits the non-injectivity of this map here to recover an endomorphism of our supersingular final elliptic curve. So let me just show you some countermeasures to this attack. The idea that we had was, instead of using only split primes, as in C-side, to enlarge the set of primes that we can use also to non-split primes. So in some sense, we are allowing all the primes to be used in our protocol. This, of course, makes things more secure, because in some sense, using non-split primes, you can actually enlarge the class group enough without losing the injectivity of the first map, and without having to walk farther down the volcano, which was one of the countermeasures that Pierrick and Luca proposed. But the drawback is that now, instead of just passing around the 2 neighboring curves, like the positive and negative direction for the final elliptic curves, you have to pass around much more information. And in fact, you have to pass around all the neighboring curves for the non-split primes, which is what we called a cloud. So you don't have just positive and negative direction, you have all the neighboring curves from your final elliptic curves in their Q isogeny graph, where Q this time might also be a non-split prime. So yeah, of course, this makes things more heavy and more complicated to pass around. And this is the reason why we started working with some improvements on OSIDH. The first one is adding level structure, and the second one is the formal approach. So adding level structure actually was the idea of sort of making computations lighter and easier, while the formal group approach sort of respond to the question of how can we make this passage of information easier, and how can we pass less data to the other party instead of sharing the whole cloud around an elliptic curve. So let's start with how to make computation a little bit lighter. So The motivation comes, in fact, well, this is just a graph that you saw before. And as I told you, one way of pushing forward the information about the action of the prime on the first elliptic curve is either pushing forward the division polynomial through your isogeny chain, which is the top one, or completing the square, or the rectangle if you want, completing the commutative square of isogeny by resolving systems of modular polynomials. So what you're actually looking for is this vertex here at the bottom. So you have already constructed the previous one, and the isogeny chain at the top is already known. So in some sense, you want to complete the square by finding this vertex here, which means you have to solve the system giving, well, the horizontal isogeny here and the vertical isogeny here. This can be done in various ways. You can actually try to pre-compute for fixed L and Q. You can try to pre-compute a sort of like one equation that gives you this square. But in some sense, we wanted to have some smaller modular polynomials here. And a way to get smaller modular polynomials is by adding level structure to your construction. But just to go a bit deeper with our motivation, there are multiple reasons why working with some higher level structure might help. Well, the first one is that while in the classical setting, we always have to be aware of the fact that once you walk one way with an isogeny, there's also the backtracking one. So when you construct your descending isogeny chain, you have to quotient out by the previous step. But actually adding enough level structure, and we will see in a moment what enough means, might help eliminating backtracking problems right away. Okay, sorry. The second one is that adding the correct, and once again, I will show you what correct means in a moment, adding the correct level structure might help rigidifying like problematic points, so rigidifying the automorphisms, and therefore getting rid of these special vertices where you have either endomorphisms and therefore cycles, or automorphisms and therefore different number of incoming and upcoming isogenies. Also, adding level structure helps shortening the distance you have to walk from the first step before being able to differentiate between the action of the two primes above Q. As I told you before, we are working with some very special class number one orders. So the action, the first vertex, is trivial. But as an example before, it might be trivial also on the second step. And even if it's not trivial, for instance, on the third level, the action of the two primes above Q might be the same, might send E to a different elliptic curve, might be the same. And finally, but not for this less importantly, modular polynomials of higher level are much smaller, so easier to use. So here is just an example. If I remember correctly, I think I stole this from Sarah's article, but it's just a toy example. I think we're working over F23. Here at the bottom, you see the classical known-oriented supersingular isogeny graph. And here we are endowing it with some gamma 0, 3 structure, which is not enough, of course, to rigidify things. Gamma y0n is never representable because gamma 0. So because the multiplication by -1 always preserve gamma 0 structure. But already you can see that at this point here, for instance, you're differentiating the three isogeny from 0 to 19. So this is a tower of modular curves that we propose to use. Well, I mean, it's a bit dense, but you don't really have to bother too much about the parameters here or the maps between these two curves. But so here's the J line at bottom. Here is gamma 0,2 structure. Here we have non-split Cartan 3 structure. And then here is their composition. So you get this modular curve here. If you want, you can construct a little bit on the right. So you can add full level 3 structure and then compose with gamma 0,2 structure. But what we actually wanted to do was to climb up from Y to what we call a Weber modular curve, which in fact is the Weber modular curve whose function field is generated by one of the 3 Weber modular functions. Here I chose F just for getting simpler maps down to the J line. And the nice thing about this is that this is a genus zero curve, so you can work with one parameter, and is level 72, which, is degree 72, which makes modular polynomial very, very small. So here is an example. Again, it's very dense. It's just a visual picture of what happens if we do the same construction, adding the level structure that I showed you before. Here we're working over F7, just because, I mean, I already with one J invariant, I got a big graph here, so I didn't want to make things more complicated than they already are. So here is gamma 02 structure, gamma non-split Cartan level 3 structure, and gamma 03 structure. You see that if you add full level 3 structure, you're already defined. And in fact, the fine modulus, the modular problem for gamma 3 is in fact representable. In fact, is representable for the n's bigger than or equal to 3. And here is the elliptic curve y, which is the one that lies below w. And then w, the graph for w was too big, so I decided to just give you the x graph instead of climbing up to w. It's too many points, but this is what you get. So you don't get cycles, you don't get endomorphisms, and more importantly, you don't actually get backtracking isogeny. So you can see already here at the bottom, but also on X, all the errors are one-directed, which is useful in the initialization phase of OSIDH. Okay, so here is just another big example, just visual representation of what I was saying. So again, we are working with two isogeny graphs, characteristic 61, and we are orienting by q square root of -7. So here you get the infinite covering with the oriented volcano. And on the left, you will get the oriented Weber structure volcano. So as you can see, all the errors are one-directed, which means that in fact, once that you leave, let's say, the first level, so once that you start descending, you can only descend the volcano, which is usual in the initialization phase because you get rid of the problem of pushing out the backtracking isogeny. And then you get some sort of appearing parameters at each level, but you don't really have to bother too much about them because once you start from level 1 and you start ascending, you will never be able to get to one of these appearing parameters here. And just to motivate the fact that I said the modular polynomials of higher level are smaller, here is just an example of a Weber modular polynomials for 2 and 3. Of course, Weber modular curves have some level 2 and level 3 structure, so this has to be constructed by walking down the level 2 and level 3 structure. But this is the polynomial that you get, which are much smaller than classical ones. Okay, so I have 15 minutes probably to talk about formal orientations. Again, so as I said before, I'll probably try to go through the background and then let's see where we end. But I can, maybe if someone connected later, I can just say there's still online the doc of David at the CM conference in Eindhoven. So if I'm not able to give all the details, you can also always refer to that. So let's start from defining what formal group laws and formal groups are. So I'm gonna use chapter 4 of Silverman as a reference, but you can find some pretty nice articles online. So, okay, so let's start with any commutative ring with unity, and let's construct his ring of formal power series in the variable tau. So a formal group law defined over our ring omega is a power series in 2 variables over omega, such that these 3 properties are actually satisfied. So we have fx0 equal to x, fxy is equal to fyx, and then you have sort of associativity. So you have fx fyz equal to fxyz. So I think you can define this in a little bit more generality without asking for commutativity. But as soon as omega has no nilpotent torsion elements, I think the formal group law is abelian by itself. Anyway, let's stick with the abelian case, and Yes, and then the two first properties, which are commutativity and fx0 equal to x, also implies that f0y is equal to y, which also means that the formal power series f is of the form x plus y plus some terms of higher degree in both as x and y. Okay, and then what is a formal group? In general, you can work with formal group laws without actually specifying the underlying group, which is the cool thing about formal groups. But in some sense, it's always nice to have an example in mind. So I'll try to give you the definition of formal group and then sort of working example to keep in mind for the rest of the talk. So if you suppose that omega is local and complete, and you pick up the variables from its maximal ideal that we denote M, then you can define a formal group associated to the formal group law that I'm denoting by curly F. I'm not sure if I mentioned, oh yes, curly F, over omega. And we denote this formal group by F omega or Fm. And this is the set M together with the group operation that comes from the formal power series F, or the power series F, or the formal group law curly F. So all these things actually, so I would probably at a certain point refer to all these things with the same name, so just use formal group. But it's nice to have this distinction in mind. So the group law, the formal group law is curly F, which comes from this formal power series capital F, and then the formal group law in general will be denoted by curly F of the set we decide to work, of the ring we decide to work with. So in so the group operation that you are defining over F omega is x plus y equal to the evaluation of your power series in x and y, where x and y of course lives in the maximal ideal of omega. And again, just to have an example in mind, you can think of any commutative ring with unity. You can take omega to be r tau, and then you can pick m to be tau or tau. And therefore, a formal group law is just a formal power series with zero constant term that makes this set here, tau or tau, into an abelian group. Yes, there's a question? Yep, go ahead.
Yes, I'm just curious why we emphasize that the underlying group doesn't necessarily exist. Is there something weird that can go wrong here?
Sorry, I lost you at the end, but the question, sorry, but I got the beginning of the question. So the reason is that you can work on formal groups in very much any generality that you want. You can work without specifying the underlying group. So this is just a remark. You can work without specifying which group you're working with, which is actually something nice you cannot do with normal groups, of course. But in general, we are going to work with the set of points of the elliptic curve. So at some point, we are going to specify the underlying group. But in some sense, you can work without doing that.
Gotcha, thank you.
This is just a remark. I mean, the remark is that formal group law works and exists without underlying group. Then you can specify it, and you can go farther. But in some sense, the recursive theory, you can do your theory without actually specifying it. So, for instance, the definition works without specifying this the set you're working with. So this was just a remark. I'm sorry if I confuse you, but if you want, just keep in mind this example here, which is probably the example I'm going to use for the rest of the talk. So we work with formal power series. We take tau or tau as our defining set. So we're just taking power series with zero constant term, and your formal group law comes from this, again, zero constant term power series in two variables. Is it okay?
Excellent.
Cool. So here just some examples. But before doing that, let me just give you a proposition that helps you determining whether a power series in two variables is indeed or defines indeed a formal group law. So this is also something nice to have in mind, and is also the way we are going to construct the formal group associated with an elliptic curve. Again, this is not the only way of doing it, but it's nice to see it in practice. So Suppose you have an abelian group with identity, and we use the additive notation. And suppose you have a one-to-one map from our set tower tau to our abelian group, which sends our identity to our identity in G. And then suppose you have a power series. You don't know yet whether this power series define a formal group law, but you have a power series zero constant term in two variables over our ring R. And suppose that these maps works well with this power series, which means that if I apply my map to two power series in tower tau, so I do TG and TH, and then I sum them in G. Well, this is the same thing as doing the group operation, or what I hope will be a group operation on tower tau, and then sending it to G. So in some sense, you just have to check that these maps respect, so these power series respect the additional load that you have on G through this map T here. So if this happens, then F defines indeed a formal group law. And here just some example. If you take G to be this full set of formal power series, so this time allowing non-zero constant terms, and then as a T map, as the map T, you take the inclusion of tower tau inside R tau, then this power series here defines a formal group law that we call the additive group law. So this is just the inclusion. Okay, so in fact, we are recovering the addition that we have already on G. It's just the sum. Now, second example, I'd be more complicated. If you take the units in R tau as your abelian group G, and as a map T, you take the map that sends G to 1 plus G, then you can look at, well, this time under multiplication, you can see what happens if I multiply two images of two elements of tower tau in G, well, once we apply the map T. So you get TG, TH equal to, well, 1 plus G, 1 plus H, which gives you this. And this is exactly 1 plus G plus H plus GH, which means that this is the map T applied to G plus H plus GH, which means that this thing here is your group law. And therefore, this formal power series here, X plus Y plus XY, defines indeed a formal group law, and we call it the formal multiplicative group law. And at a certain point, again, I will drop probably low. I will just talk about formal groups, but just to keep it a little more general. And finally, which is the example we are most interested in, if you have an elliptic curve over some field L, over L, which is a fraction field over tau, you can construct a map, and we will do it in a moment, from tower tau to the set of points of E over L, and find a power series exactly in this way as we did before, and therefore define a formal group law of the elliptic curve, and therefore construct a formal group associated to the elliptic curve. But before doing that, let me just spend a few words on the homomorphisms of formal groups. In some sense, we will construct a category of the formal groups associated with elliptic curves, so we actually have to translate isogeny also. So suppose you have two formal, but let me just do it basic general definition first. So suppose you have two formal groups, curly F and curly F prime, formal group laws, sorry. Then an homomorphism from these two formal group laws, or formal groups, if you have decided an underlying set, is once again another power series, again with zero constant term. The reason why we all have zero constant term is that all of these operations are actually compositions. And of course, if we allow non-zero constant term, we have a problem in evaluation. Okay, sorry, there's a question in the chat. The field L is disturbingly huge because of the tau. Yes, everything will be very, very huge. We'll see in a moment that in fact, we will get way more things, way more points, and way more endomorphisms also. So yeah, the object is huge. Yeah. Does this reply? No question. Okay, so yeah, so the endomorphism is just another power series. Once again, just repeat it once more. We take non-zero constant terms because we want composition to work. And so we actually want U of fxy So we actually want this power series to respect the formal group law that we have on F and F prime. So we want U of F to be equal to F prime, evaluating the image under U of X and Y. So in other words, you just want this map here sending G to UG to define a homomorphism between the underlying groups once that you have fixed some underlying groups for your formal group laws. So just to give you another example, just keeping in mind the tower tau example that I was showing you before. So suppose you have two formal groups, and suppose they are associated with these two formal power series in two variables, and you have these two maps, T1 and T2, to your two abelian groups, G1 and G2. Then what happens is that if you have a group homomorphism between G1 and G2, so these two are just classical abelian groups, so this is classical homomorphism between groups, and you have a power series U in tower tau, then you can verify whether U is a formal homomorphism or not, just by verifying that it behaves well with respect to the homomorphism side from the two abelian groups. And I'll show you in a moment a picture, but in some sense, you want the commutative square to actually commute. And well, this is the commutative square. So, you know, the horizontal lines are the construction I showed you before. So you start from tower tau to some sort of abelian group. So T1 is actually the one-to-one map that verifies whether F1 is a formal power group law, or not. And the same happens for T2. Then you have a classical homomorphism between G1 and G2. And to verify whether U is a formal homomorphism or not, you just have to verify whether this diagram actually commutes. And let me just give you some other examples. So suppose, for instance, that G1 and G2 are the same group under the same maps, T1 and T2. And therefore, you get the same two power series defining formal group laws, F1 and F2 will be equal to F. And then we just want to see how multiplication by n actually works. So this is, of course, defined recursively just by setting multiplication by 0 to be 0, multiplication by 1 to be the identity, and then I plus 1 U equal just, this shouldn't be U actually. I'm sorry, there's a typo, but multiplication by I plus 1 should be multiplication by I plus, where the plus, of course, comes from the the formal group law plus tau plus 1. And if you want to see this working in the additive formal group, well, remember that the map T that defines the additive formal group is the map the inclusion from tower tau to tau, and therefore multiplication by n is equal to this homomorphism here, which is the multiplication by n on G, tau G, which is TG, which has to be equal to TUG, which is multiplication by n, which means that the formal multiplication by n is actually just classical multiplication of tau by n. And if you do the same for the multiplicative formal group, then you will get classical exponentiation by n. Okay, let me just accelerate a little bit to conclude in 5 minutes. So let's get to elliptic curves, the interesting bits. So we actually want to construct the formal group associated with an elliptic curve. And the way we do this is we parameterize elliptic curves in order to work locally around the point of infinity. So we take classical elliptic curve, define the classical Weierstrass equation embedded in P2 over some field K. So you get a classical equation here. And then you start working locally in a neighborhood of the point of infinity, where you can choose parameters that we call z equal to minus x over y and w minus z over y. And therefore, which are like local parameters around O. These are functions defined at O with zeros of degree of order 1 and 3. And if you look at these two parameters here, they actually satisfy an equation, which is this one here, that you can actually use to Hansel lifting W in a power series in Z. So in fact, Z is a local parameter, is a uniformizer at O. And what you get is a local point in a neighborhood of O. And we have this lemma here, which we're going to use later, which says that whenever you evaluate your Weierstrass equation in tau minus 1 and this new power series W tau, you get 0. And vice versa, if you have two zero constant term power series and they give 0 in the Weierstrass equation, then the second one, G, is actually the composition of the power series defining omega with F, which actually means that if you look at this Weierstrass equation over the closure over tau, and you fix F, well, this is a cubic equation, so you're actually getting 3 solutions. But what this lemma tells you is that only one, exactly one, lives in tower tau. Okay. And then we are finally able to construct the formal group law associated to an elliptic curve. So what we do is exactly what I showed you before. So we start from tower tau, we embed it into EL, which is this big field. And then we're going to steal the group law from the elliptic curve, exactly as we did for the additive formal group or the multiplicative formal group. So once again, we start from some field K. We construct a quotient field of K tau, and we consider points in E of the instruction field. Okay, and then by the lemma of before, you get an embedding of tower tau inside EL, which is given exactly by taking taking a power series with 0 constant term and sending it to the point F minus 1 WF, which is exactly the lemma of before. And then if you do the same computation that we did in the examples for the additive formal group or the multiplicative formal groups, what you get is, once again, a power series in 2 variables with 0 constant term and of the form of the desired form. So x plus y plus higher terms in both x and y. And this is actually the formal power series, the formal group law associated to our elliptic curve E. So once again, I did it using an example. So I use it using this one-to-one map from tower tau to our group, but you can actually work in a little bit more generality. And what happens is that if you take any complete local K algebra, then you can construct a formal completion of the around O, and then you get an isomorphism from the maximal ideal and the completion over R, the formal group of E over R. And this isomorphism is exactly given by this map here, which is, well, send Z to Z and omega Z. And well, let me just conclude. What is nice about that is that, in fact, the new category that we are constructing also takes care of isogenies. And in fact, you can prove that from every isogeny between 2 different elliptic curves, you can construct a homomorphism or formal homomorphism of formal group laws. And in fact, a formal homomorphism of the 2 formal group laws associated to the 2 elliptic curves. And the way to do that is, well, you just consider your isogeny, where you can actually pick your 3 homogeneous polynomial of given degree D. And then if you look, for instance, well, F1 and F3 will not vanish at the origin. We always work locally around O. And then if you take this quotient here, well, this happens to live in the maximal idea. And therefore, you can actually expand it as a power series in tau, and therefore getting your U, which is, the U that defines, in fact, the formal homomorphism. And in fact, you have this correspondence, which is given by this proposition here, which tells you that whenever you have an isogeny, then the U constructed this way actually defines a formal homomorphism between the 2 formal group laws. Okay, I'm gonna conclude that there just by giving a couple of examples of, well, what happens, for instance, if we consider multiplication by -1. Then if you look at the addition law over the equation defined by Z and W, then you can actually work out that -1 times TG, where T is this embedding of tower tau inside DL, is equal to, well, -1, well, this is just the image of T, and this is just using additional laws on the equation of the elliptic curves. And therefore, by the lemma that I showed you before, since this is a point in EL, well, this last term here has to be the composition of omega with the first one, which tells me that this object, this big this big point here is actually the image of the first point, which in turn means that multiplication by -1, the formal multiplication by -1 is given by this fraction here, which can be expanded in a power series just by working the geometric series of the denominator and multiplying by -τau. And so you get this one. So yeah, similar calculation for 2 gives you 2τ plus higher terms. And in fact, this is more general because, as David told in his talk, formal multiplication by n always have leading coefficient by n. And then I had some other things to say, but let me just get to the point of how to use formal groups for OSIDH, and then I promise I'll stop. So the idea is to basically do the same thing that we did with classical endomorphisms, and then push forward through our, well, this time formal isogeny chain, push forward our formal endomorphism to the final elliptic curve. And in some sense, we would be able to, once we push forward the endomorphisms on the final elliptic curve, to pass around, instead of all the information about the neighboring curves, to only pass around the formal groups, which are more compact. And in some sense, this is where we are actually working with, because the point is, even if we pass around the former group, which seems reasonable, because as David said in his talk, there are no known attacks to which enables to recover, the classical isogenies or the classical endomorphisms. Well, the point is that we're not really sure yet on how to use formal endomorphisms to cut out the information that we need, which means in particular to cut out information about the action of the endomorphism on the L torsion of our super-singular elliptic curve. I'm stuck here because I've already took probably too much. I'm sorry if I went really too fast in the last slides, but I actually wanted to give more information on the background and more like theory to be able to construct this formal group. And yeah, if you're interested, and you can actually watch online the CM talk of David in Eindhoven. Thanks.
Thank you very much for a great talk, Leonardo. If anyone has any questions, please just type them in the chat or unmute and scream them out. Maybe I can ask first. So
sure.
I think you maybe kind of answered this at some point, but could you like repeat what was like the motivation for, or what is the motivation for using these?
Yeah, well, the point is that, let me just go back to this. So the point is that for OSIDH, well, let's start from the classical one. You actually have to pass around information about the neighboring curves. If you add non-split primes, so for instance, you're working in a volcano, which is, I don't know, the 2 isogeny graph or a 3 isogeny graph. And you get to a certain level in the classical sense. Using split primes, you can actually do some sort of seaside at level n. But then what you can do is also add the use of non-split primes to enlarge this class group without leaking too many information. So you can actually look even farther down the volcano to get a sort of like bigger circle using non-split primes. So in a certain sense, you can actually use in the key exchange even 2, which is the prime defining the isogeny graph. But for doing that, you actually have to pass around way more information. So you don't have just 2 directions, but you have all the neighboring curves in the 2, 3, or whatever the prime is, isogeny graph. So in some sense, you can think of this, well, it was nice to have this countermeasure, because in some sense, it replied to a question that Luca posed me like probably during my first year of PhD, which was, can we see, well, we can definitely see seaside as an instance of OSIDH, but can we also see SIDH as an instance of OSIDH? And with this, yes, you can, because you can use 2, for instance, or 3, which are the 2 primes using SIDH. The thing is that if you want to use this framework to recover SIDH, in some sense, you have to pass around all the information about the neighboring curve, which in some sense means you have to label all the supersingular isogeny graph. In some sense, you have to tell, okay, I'm here, and all these edges correspond to, so number 1, number 2, and number 3, for instance. So in some sense, you're doing C-side SIDH with a completely labeled supersingular isogeny graph, which in some sense is great because you don't have to pass, the points around, but it's a huge work because you're working over like a huge supersingular isogeny graph, which doesn't make any sense, right? So, in theory, you can recover SIDH, but in practice, it's impossible because you have to pass around too many information. Even in our setting, so without thinking about SIDH, even in our setting, we actually have to share information about, we call this object a cloud, which is basically a volcano around the final elliptic curve. And in some sense, we have to pass around at least the information of the first 2 levels or all the non-split primes, which means that since we allow primes up to, I don't remember exactly the parameters, but around 200 or something like that. I mean, if you have a prime of the size of 200s, you have to pass around information about 200 plus 1 neighboring curves, plus all the 201 neighboring curves for each one. So you have to pass around a lot of information. So it's not a problem in terms of security, it's just a problem in terms of the amount of data that you're passing around.
Yeah.
And so the question was exactly this. So how can compactify this information here? So is there a way of passing around just, the former groups, so like 1 or 2 power series up to a certain precision that cut out the torsion at this elliptic curve, which means we don't really have to pass around all the neighboring J invariants, but we can just pass these 2 elliptic curves and then, these 2 power series, and then the other party will be able to find by himself the neighboring curves. So this was the point. So sorry, I forgot to mention, but the nice thing about OSIDH is that it works solely with J invariants. So we don't work with rational points to construct isogeny. So yeah, I mean, passing around a cloud is a countermeasure, but in some sense it makes the already infeasible OSIDH even heavier and more complicated. So the idea of using former group was find a way of passing the information in a more compact form. And a more compact form would be a sort of like approximation of a power series, or up to a certain precision that allows to determines the neighboring points from the other party without sharing this information at first hand.
Okay, and the coefficients.
Does it make more sense?
Yeah. That's a good explanation. Thank you. So the coefficients of this power series, they don't like how big are they? I'm not so very familiar with this.
Yeah, this is more or less where we are at. So they're not big,
Okay.
and also we don't really have to share. Well, as you can see, for instance, for multiplication, this is just n plus higher term. If I remember, well, let me just see. Well, the former power series defining the group, the power series defining the former group is this one. So it has are polynomials in A1 and A2, and you can actually prove that also for isogenies, the coefficients are polynomials in the Weierstrass coefficients of the elliptic curve. And also, I mean, where we are at is also either find like a way of using formal endomorphism to get out the torsion, but also understand which kind of precision we want. So I'm a bit sketchy with this reply, but I'm not really sure how far you should go to share enough information.
Okay.
But yeah, the coefficients themselves are polynomials in the Weierstrass coefficients.
Yeah.
There's actually a nice exercise if you want to just, for instance, to prove that the endomorphism ring of the formal endomorphism ring of an ordinary elliptic curve is at P. You can actually prove that the endomorphism ring of for ordinary curves, the formal group is isomorphic to a multiplicative group. And once you're there, you can actually prove that all the endomorphisms for the formal multiplicative groups are actually of a certain shape. And this gives you, in fact, the answer that, this gives you explicit, not just the answer, it's not a proof, but it gives you explicitly the polynomials for for these homomorphisms.
Okay, yeah, thank you very much. See, there's a few other questions
sure.
in the chat now too.
In
So
the chat.
yeah, so June asks, is it possible to use higher dimensional formal groups laws on, say, genus 2 curves?
Well, honestly, I mean, we're still working on the genus 1 case, but I think in some sense, yes, it should be possible, definitely. I'm not sure how to answer yet because, you know, we're still working on the elliptic curve case, but yeah, you should be able. I'm not sure how it will be, but it would be great actually if it worked. Actually, one of the things that I wanted to do was also try to see how OSIDH works in higher genus. But yeah, I'm not sure yet. still finishing working on genus 1. Sorry.
Okay, thank you. We also have a question from Damien Robert, who asks or asks a question. So for context, he says that...
Should I read it? Oh, yeah. I can read it. Yeah. So the formal group of an elliptic curve is equivalent to the connected component of its PZ visible group. So a formal group is like P to infinity level structure. Did you try exploit the PD visible viewpoint for your computations? Sorry, the PD visible viewpoint for your computations with formal groups? No, not yet. It's definitely something we have to do. Yeah, we are still trying to understand how it works, but definitely there was a slide about that at a certain point. Most of them, but yeah, in some sense, one way we're looking for solving this problem of understanding how it cut out the torsion is to extend formal endomorphism, because of course they work in a neighborhood of infinity. We actually want to extend it to, well, this discrete torsion group. And in order to do that, we're actually trying to look, but again, this is very much work in progress. It's the very last phrase of the talk. We're actually looking for lifting things in ZP. So I guess this is what you would do, probably suggesting to ZP and use some sort of interpolation to get this action on the L torsion. But yeah, this is what we are currently doing. So in this moment, does this reply? Thanks. Thank you very much. Yeah, this is exactly, sorry, I skipped like the last 4 slides, but this is exactly what we're working on now.
Okay, very cool. If there are no more questions, I think we'll say thank you to you again, Leonardo.
Thank you very much, you.
Also, in the next week, or in 2 weeks, we'll have Tomoki Moriya giving a talk on some mystery talk for now. Some new fresh research coming, so stay tuned for that. And yeah, I'll turn off the recording now.